Welcome to 1007 ICT, 1807 ICT, 7611 ICT Computer Systems and Networks. This is Lecture 7, Operating Systems. Last time we covered the idea of addressing. We talked about little and big endian. We talked about the differences between primary memory, secondary memory. And then we had a chunk of stuff on data errors and how we detect errors and how we correct errors. And that was to do with parity and the Hamming code stuff. You'll see more information about that in the workshops coming up. So in this time, we're going to be looking at the history of operating systems, what they are, what they're tasked with, why we have them, the idea of bootstrapping or starting up a machine, the kernel, process management, CPU scheduling, dispatching, memory management, virtualization. There's a whole bunch of stuff that we look at here. But this is to do with when we make a machine available to a person, we want that person to be able to use that machine efficiently and effectively. If I just give you a piece of hardware with no software on it already, it's going to be very difficult for you to use that effectively. So you will get a machine with Windows on it, or Mac operating system, or iOS, or whatever flavor of operating system that it has on it, and that will help you ideally to use that machine more effectively. And there's a whole bunch of those operating systems. So we'll talk a little bit about the history of those, and you'll notice that, again, these concepts, this is more about understanding and learning about this stuff. So again, there's not really a lot of process here. It's more about, well, why did this evolve? How did it evolve? And you'll see, basically, there have been a lot of improvements over the years, and we're benefiting from those at the moment. So the first thing is that if you have a computer, it doesn't matter if it's the biggest or the fastest computer in the world, it is of absolutely no use to you if you can't use it efficiently to give you some output. All right, so if you did not have an operating system of some kind, you would have to physically interact with the hardware to make it do what you want. All right, that's typically fairly involved, especially if you want to write or run a program that's a little bit more involved than just typing some text in. Okay, so an operating system allows the users to load and run different application programs and to effectively use the underlying computer hardware. You can still have a computer without an operating system. Some systems do have that, for example, some specialized systems, but then you need to be well trained to be able to use that particular piece of hardware. Okay. So the operating system is the glue that holds everything together, and you can think of it kind of like a government. All right, so by itself, the government really doesn't do anything, right? But it provides an environment where things can happen that will benefit, ideally, the people that it's looking after. So without an operating system, users would need to physically load the computer with whatever program it was to run on, and that might not be such an easy task, just the loading of it, power it up, and then reboot it to end the program. So you could typically only run one program at a time. How many programs do you run at a time on your machine at the moment? Lots? Yeah, I wouldn't even really put it up a limit on it. You just run lots, open up lots of tabs, run lots of different programs. Depending on how powerful your computer is and what kind of operating system you have, you may be able to do that or you may not be able to do that. Depends on the environment. So operating systems are really useful, and we pretty much, that's our experience of the computer. Like if I tell you that I've got here a Mac, then that will tell you something about typically how I'm going to use that environment. I'll be using the Mac operating system most likely. If I've got a Windows machine, I'll be using the Windows environment and so on. Here is a computer, and you look at the front of that, and you see those switches on the front? Those switches are for you to put information into the computer. Does it have a keyboard? No? Would you like to be interacting with this machine to do your assignments? Probably not. All right. Is it still a machine or a computer? Can you still work with it? Absolutely. Right. It's just not as efficient to work with it for most people. So looking at the history of operating systems, the first computers were programmed in machine code by using those switches on the front of the panel, ones and zeros. That sounds very time-consuming and very error-prone. It's really easy to make mistakes in that environment. So in the 1950s, data was entered using punch cards or paper tape. So there's a big improvement. We can now store the program somehow on some format, and we can just plug that into the machine in some way. So paper tape and punch card, does that sound slow to you? Yeah, it's pretty slow compared to what we're using these days. What you could do, though, is you could group a batch or a bunch of jobs together, and you could run them as a batch. So you just throw one job, two jobs, three jobs, four jobs at the same machine. As long as the program that needs that information doesn't change, you can just do them one after the other. So you can kind of get a performance improvement there. If you need to change the program, then you have to stop that batch and do a new batch for the next program. So in the 60s, the need to allow several users to access the computer at the same time via online terminals led to the development of something called time-sharing systems. And you may be familiar with the idea of time sharing, for example, with, I don't know, units or apartments, where you buy a timeshare an apartment and you get 4 weeks of a year, right? And someone else gets the next 4 weeks and so on. So you share this resource. It's a similar kind of idea. So later, the need to be able to run several jobs at the same time led to the creation of multitasking. So they're slightly different things. There's this idea of time sharing and then multitasking, and the operating system is responsible for sequencing the execution of these jobs so they get the resources they require. So there's an extra little bit of information there. When you have a job on a computer, it needs some resources. The most obvious one is that it needs the CPU. Okay, so in older machines, you have one CPU that can do one thing at a time. What kind of computers are we working with these days? If I go to the shop and I buy a machine, what does it tell me about cores or those kinds of, that kind of terminology? 2 cores, 4 cores, yeah, 8 cores. So what that's really saying is that there are multiple processing units inside this chip. In the old days there was 1, now we might have 8. So we could technically be doing 8 things at the same time. So we're doing things in parallel. Does that mean things are faster now? Possibly, yeah. Depending on the parallelism that's in there, the chip might be the same speed, but if you're able to do 8 things at a time instead of 1, there should be an improvement in what you can get done in one time unit. So that's one resource, but there are other resources. For example, the memory, right? There might be devices that you're waiting on, for example, like a disk drive. So resources are not necessarily just the CPU. So in the 70s, the need for microcomputers to support file systems led to the development of disk or DOS-based systems. So you've probably already heard of DOS environments, the old text-based kind of environment. What I want you to think about with that statement there is before that point, we did not have a file system. Just think about that when you think about using your computer. When you work with your computer, you tend to work with files, right, or programs. Imagine that there is no file system. How do you organize your stuff? Is that a big change, do you think? Absolutely, right? So we're benefiting from that, but at some point, the things that we take for granted, they were not there at that point. So they developed those over time. So in the 1980s, Xerox invented the graphical user interface, which pretty much is, what we use these days. Graphical user interface is nice and easy to use. You can double click on things, you can move stuff around. Typically it's less powerful than, say, the command line, because you can't necessarily implement everything at the graphical user interface level. You might have more powerful commands that you have to type in because you can put more variations on those commands. So later, distributed operating systems were developed for computers that could run tasks on several interconnected processors. So now we're not only doing work on our machine, but we're distributing the work to other machines somewhere else. Does that sound a little bit like the cloud computing model? Yeah, so that's probably morphed into that model from the older environments. So in the 80s, those evolved into the network operating systems, and that makes other computers on the network appear as an extension of your computer. An example that you probably run into is when you're in the lab and you look at the drives that are attached to your computer when you've logged in. You'll see C drive, probably, maybe there's a D drive, and then there's an S and your student number drive. Right, you're all familiar with that one, so you have some space that you can store stuff. Is that drive actually on that computer? No, it follows you around. Wherever you log into, it just connects to wherever that drive is. And so that's a simple example of this network type environment where actually the resource that you're using may not be right here, it may be somewhere else. Can that be problematic? Yeah, if the network is down, you don't have that drive or you don't have that resource, right? So as long as the network is operational, that's actually really good, but there may be some downsides to that. Last one we look at is a real-time operating system is used in embedded computers for controlling advanced electronic or mechanical processes. So some example devices are a self-driving car, a router, a microwave oven, depending on the device you have. So the self-driving car is probably the most obvious one. So a real-time operating system, what it does is it says, okay, you want a response. I will guarantee that you get a response in this time unit. Does Windows guarantee that? What do you think? Not really. Depends on what you're doing. Yeah, sure, it'll say, look, I'll give it to you in roughly this time, but I can't guarantee that there isn't a higher priority process that will take priority over what you're trying to do. For example, if I'm streaming stuff, typically I want that to be the highest priority because I don't want other things to interrupt the streaming. Yeah? Does the streaming slow down sometimes anyway? Sure, right? Because it's not a real-time system or a hard real-time system. What about with a car, a self-driving car? Do you want the self-driving car, I don't know, it's driving and then it decides that it needs to defragment its hard drive? And while it's doing that, it's not looking at the road. Does that sound like a good situation? No, right? So in those environments, you want the operating system to be able to guarantee that if you have a request, I will get back to you within this time frame. And so then you can make better decisions. And it's really obvious with like a self-driving car where the outcome would be bad if you didn't have that. So you've just talked a little bit about the different kinds of things that have been added or developed as we've gone through the history of operating systems. And you can see the need for these as well, right? Depending on what time frame we're in, they needed a certain improvement. Here is a set of punch cards on the left, and then there's a big bunch of punch cards on the right. You can probably see some issues with the punch cards. There's a whole bunch, really. One of them is, you see the little holes in the punch cards? That means that a machine has to punch the holes in. Is it possible that it doesn't punch the holes properly? Sure. There was a thing, I think, in the United States where they had the ballots in the elections and they had some problems with punching holes. And so mechanically there's some potential issues. The reader, can the reader have some problems? Sure. Can the card be damaged? Yeah, pretty easily actually, if you fold it or something, if it gets wet. The one on the right there is interesting. Imagine if you push that pile of paper over. How long would it take you to reorganize the data? Quite a while, right? And they have to be numbered so that you could work out which one's which. So again, there's a lot of limitations with this stuff. But it is certainly a way to store information and process it. It's just slow and it has some issues or potential issues. Looking at the operating system, the overview of the different layers that are in it, typically it consists of a memory resident kernel. That's the thing that just works all the time basically, and other memory non-resident systems programs, and they're typically arrayed in layers. So if you start at the bottom, you have the hardware. Okay, so that's the actual physical stuff. Above that you have the kernel, that's the thing that's running all the time, and we've kind of looked at that as, you know, at the CPU level, that was the loop, the fetch, decode, execute cycle. Does that make sense? That's the kind of process that we looked at a low level. This one's probably a little bit more involved, but it's a similar kind of idea. It has some device drivers, so if the top layers, for example your program, wants to talk to one of the devices, it doesn't necessarily know exactly how to do that, so there's a little program sitting here at a lower level that says, okay, you want to write? Okay, I know how to write to this one, so I'll do that. It translates your instructions. Is that good or bad, do you think? It's good because your program then doesn't need to know how to write to every single different device on the market. Is that even technically possible, do you think? If I build a new device today and it works slightly differently, your program has to be updated. As opposed to just having a new driver that you slot in where you just talk to that one and it does the translation for you. Above that is a service layer. It contains a set of functions or APIs, application program interfaces. If you do any program, you'll run into those. It's a library of calls that you can use. It's how you can talk to the next layer. So it has a set of functions called by application programs and the command layer for loading, managing, and executing programs. So when you double click on something, there's a call to this service layer that says, oh, you double clicked, that means you want this program to open, I know how to do that, and I'll execute this open call on this particular program. Okay. The command layer is above that, and that's typically a shell or a graphical user interface, which, like I said, you double click on something, right, or you type some command in, and that will be filtered through the service layer, and it says, okay, you want this thing, I'll do that thing. Next to that is the user application, so those are your programs, and they can also talk to the service layer. So one of the most common things that you probably do with that user application level is print. Alright, so what happens is your program says print, the service layer says, okay, there's a print operation that gets translated somehow, and however the printing is configured on this environment, that printing will happen through that process. Does your program need to know how to do the printing? To some extent. It needs to know what it wants to print, for example, but it doesn't necessarily need to know how to do the printing. It just says call the print function. So these are the different parts. Can you see that they're fairly modular? And we can switch some of them out potentially and replace them with other things. And so you're getting I guess a model, and looking at this model, you'll see this kind of model in other places as well. It's kind of built up in layers. particularly when we talk about the networking. And when we look at these layered environments, typically we're making each of the layers simpler than they would be if they were just one big chunk, right? And that's one of the benefits. So when we want to start up a computer, we have to go through a certain process. There's this thing called a bootstrap loader or a mini loader or initial program loader, or there's a bunch of different names for it. It's stored in the BIOS or the ROM, depending on the machine that you have. Typically, probably it's BIOS these days for the kinds of machines that we work with. It looks for the operating system program in a fixed location on some device, and then it loads the operating system into RAM. Well, it doesn't actually load the whole thing. How big is Windows these days? Gigabytes? It's pretty big, right? So it doesn't load the whole thing in memory at once. It just starts with a little bit, and then it grabs the things that it needs as it needs them. Yeah? Once it's done that loading, or at least the initial part of it, it transfers the control to the starting location of the operating system. So it basically just says jump to the first location and start running it like a program. Is your operating system most likely a slightly different program than, I don't know, some of the other programs you run like Microsoft Word? Yeah, it has some other responsibilities, so probably it has a higher level of privilege than some of the other programs that you might run. Does that kind of make sense? You probably want to separate some of those things a little bit. And then there's a loader program in the operating system that's used to load and execute other programs, like the user programs, for example. There's a diagram down the bottom here. I'll talk about bootstrapping here. I'll just draw it, I think. So when you're bootstrapping, when you're starting the machine up, so there's the process for that is here in the ROM or the BIOS. There's a program counter that points to a fixed address in this space, and the program counter starts from there. So you remember the program counter from the CPU? It's where the address of the next instruction is. So the program counter at the start just says start up the top here and go through the list, the checklist, the things that you have to do. The bootstrap loader directs the computer to copy data from some place on the disk. Now this is the initial part. It's just enough to load the rest of it. So you put that somewhere on the disk in a fixed location, and then that thing will be loaded into RAM. And then once you've loaded this part into RAM enough to actually run the operating system, the program counter, which was over here, is now pointing to the start of this. You just change where it's pointing to. So you tell it, okay, you finished doing what you were doing, now go to the next program, which happens to be the operating system. Okay, so you can change what you're pointing at as you go through. Does that mean that we can have different operating systems on different computers? Sure, technically, if you put a different operating system in at the right point and it's able to load up properly, it should work, right? So you can actually run different operating systems on different environments as long as they're configured. So the kernel. At startup, the operating system kernel is loaded into RAM, so we talked about the bootstrap loader already, and it runs continually while the computer's powered up. It's this basic loop. If you think of a game, there's a game loop. This is the computing loop. It contains essential services required by other parts of the operating system and applications, and it does a whole bunch of things. Right, so if you're thinking about it like there's a loop and it says, if I'm at this stage, do this thing. If I'm at this stage, do this thing. And there's maybe some things it decides based on what the condition of the machine is. So one of the things it does is CPU management. So it needs to schedule things. It needs to deal with interrupts. We talked about interrupts briefly before. Right, so an interrupt is something that machine's doing something, and one of the devices or something needs something to happen. So it generates an interrupt, and then the CPU stops, processes the interrupt, and then continues with what it was doing. So there needs to be some way for this kernel to deal with that. Process management, so there's this idea of multi-threading, we'll talk about very quickly. Inter-process communication, if you want these jobs to talk to each other. Synchronization, sometimes one job has to wait for another one. Alright, so it's like a computation. When you're doing a computation, sometimes you've done one step and you can't do the next step until you've worked something else out, right? And so you might have to wait. And you can do that through some synchronization forms. Memory management, so you can allocate memory. When you run a program, do you think it gets all the memory in the computer? Probably not. It could. In the old days it might have, but in these days you want to run multiple things, so giving it all the memory would be probably a bad idea. You give it a fraction of the memory, for example. So it's allocation. There's also deallocation in there, so once it's finished you want to get rid of it. Swapping. So one of the things we'll talk about as well is if you're thinking about the computer that you have, and let's say it's got 2 gigabytes of RAM, right? So it's not very much, for example, these days, but let's say it has 2 gigabytes of RAM, and you want to run some programs. If you want to run Photoshop, is Photoshop pretty big? Yeah, it might actually take 2 gigabytes of RAM. So if you want to run Photoshop and something else, and let's say Photoshop takes 2 gigabytes of RAM, can you run both of them at the same time? Normally, no. So what you could do, though, is only run part of Photoshop and part of the other one, right? And then load in things as you need them, right? As long as that's configured properly, you can do that. And so you might need to swap between stuff that's on the disk that I need right now, or stuff that's in memory, right, that I don't need right now that I want to kick out, and so on. User management, access control, login, security. Now on a single user machine, this is probably not such a bad thing, right? But if you're using a multi-user machine or you're sharing it with other people, you're probably more interested in this kind of security, right? And typically we are moving towards more secure environments. Okay, you can probably see the need for that. I/O device management. So I/O means input-output. So device management, access control, who gets to use what and when. Are you able to print? Right? Are you able to use the disk drive? Are you able to use this particular device? And then there's file system management and secondary storage. So all the stuff to do with opening, closing files, saving them. There's a whole bunch of stuff that fits there. So pretty much anything that you want to do should be covered in this list of things in terms of how you interact with the computer. So now we go through them in a bit of detail, not in much detail, but a little bit of detail for each of them. So the first one is process management. A process is basically a job. It's a unit of executing software that's managed independently by the operating system. So if you're looking at the operating system, it'll say, I have this job, and I have this job, and I have this job, right? And they'll all be separated. Now internally, each of those jobs may have multiple parts, but the operating system sees them as one thing. So you have most programs will run as single processes. That may be changing over time, and there are also multi-threaded programs that run as multiple processes. So I'll just jump out here to give that distinction. So normally, when you have a single-threaded process, what that means is there is one thread of control. So what I have is one program counter, and my program counter goes through memory, and it just basically, it might be in a loop here, for example, for a while, and then it goes through. But there's only one program counter. And maybe there is some data over here, and it uses that data, for example. Does that make sense? With a multi-threaded process, you might have program counter 1, program counter 2, program counter 3, and so on, and they are all running in different locations. Inside this job, though. Okay, so we have multiple threads of control, multiple things happening at the same time. Can you see any potential issues with this, as compared to this one? This one's safe, right? Nothing can really go wrong. You're running in your own space. There's only one of you. What about this one? There are 3 people running around. Can they hit each other? They can potentially hit each other, and they can interfere with each other in terms of the resources. If there's only one data chunk, and this one wants to use that thing, and this one wants to use the same thing at the same time, is that potentially a problem? Sure. If I'm trying to write and you're trying to read, we're interfering with each other. So there's a bunch of things that you need to be aware of when you're working with this multi-threaded environment. It's more complicated, basically. But you can see it's definitely possible if I have multiple program counters, right? There's just individual ideas about what our next instruction is. So that's just a little visual version of the difference between single process and multi-threaded process environments. So a process, because it's a job, it's a thing, it can request and receive hardware resources and operating system services. So it might say, look, I need the hard drive because I want to write something. Okay, if I'm using the hard drive, can someone else be using the hard drive at the same time? Probably not. There might be a queue of things that we have to build then, right? So we just sort of store them until they can be processed. So process management is the core of the operating system services. The operating system creates processes, it schedules their access to resources, deletes processes, deallocates resources, and it does a number of things around processes or jobs. It monitors the activities of each process because some processes can run into each other, like I showed you with the multi-threading version, right? So you can have the things interfering with each other. And so there are some synchronization problems, and I'll show you a couple of synchronization problems, at least one. Here is I'll show you a non-programming one. So here's a bridge, and it's a one-lane bridge. And here's a piece of road, and here's a piece of road. And here is a car. Now I did mention that my drawing is terrible, right? But I think you can see it's a car. And then on the other side is another car. Now this car is a really fast car, right? The synchronization problems you can have with this environment is, well, this is a really fast car. You can see it's pointy, right? If I had a red thing, I would color in red. But imagine that there is a steady stream of these, the fast ones on this side, and they always go first. What happens to this guy? He has to wait every single time. There's only one lane, right? So if there's an infinite number of these cars, which could happen in a computing environment, this car will never get to go, because it will never get access to this bridge. Does that make sense? So that's a potential problem. What about if, well, he says, look, bugger it, I'm going to go anyway, and this one goes as well. What happens? If they meet in the middle here, they're going to hit each other, crash, and you'll have a different kind of problem. One of them is that nothing happens on the left-hand side. This one is, well, something did happen, and now we've got a problem. Maybe the data is incorrect or something. But in this case, the two hit each other and blew up, basically. So those are a number of different synchronization problems, and they're synchronizing on a shared resource. In this case, it's a bridge. In the computing environment, what could they be synchronizing on? Any of the devices, yeah, the drives, right? So there's a bunch of things that could go wrong here. As long as they're sharing a resource, you have the potential, if you have multiple things running around, to interfere with each other. So the operating system also provides inter-process communication that allows the processes to communicate if they need to. So I've done something and you need to know about it. I have to have a way for you to know about it. There's different models for doing that as well. So single process versus multitasking. So some operating systems only permit one user program to be executing at any time. That doesn't sound like most of our modern operating systems. Would you agree? Typically, you can run multiple things at the same time, and they kind of proceed. So that might be something like MS-DOS. Although you might actually be able to load multiple programs into memory, but you might not be able to run more than one of them at a time. So there's only one active. So when the program is finished, or the user switches context, the control is transferred back to the command shell. Well, when it says that the user switches context, it means that the program gives the CPU up by itself. All right, so it just says, okay, I no longer need the CPU for a bit. When an application program begins executing, the operating system grants it exclusive use of all unused resources. It's the only one that's running. You can have everything. No one else, you won't interfere with anyone else. Okay, so in this environment, the CPU is often idle, waiting for the completion of input and output. So I'm the only one running. I'm not giving up the CPU. I'm writing to the drive. That's very slow. While I'm writing to the drive, no one else can do anything. So potentially someone else could have been processing at that point. So this is not necessarily very efficient, and also it's reliant on that single process to be nice and give up the CPU. Is it possible that it just keeps the CPU forever? Yeah, used to happen in some older programs, right, where something went wrong and it just never give up the CPU. What would you do in that situation? You would switch off the machine, turn it back on, right? Because there's no way to stop it from getting off the CPU, or to keep it on the CPU. So multitasking operations allow multiple programs to be executed concurrently. So while one program is waiting, another program can be doing something. That's a big improvement because you're now utilizing the CPU more effectively. So the CPU typically switches rapidly back and forth. So it does one, does the other one, does another one, and so on. And it just switches in a very fast way. And that's called time slicing. And the process of selecting which program to run is called scheduling or dispatching. So what you're doing, you've got a bunch of jobs that you want to do. You give them each a little slice of time, one after another, and you can schedule how they operate. So you can say, well, this one is the most important. I'll run this one first. This one is second. This one is third. Or you could schedule them a completely different way. So there's different algorithms for scheduling those things. Just talk really quickly here about this visually, because I think it may be a little bit abstract, what we just talked about there. So I've got a program here, program 1. It's executing. It has the CPU. No one else can use the CPU at this point. It says, look, I've done my executing for now. I want to do some input and output. I want to write something to the drive. The environment says, okay, you're waiting for input and output. You're not using the CPU. I'm going to start program 2 up. They're ready to go, and I can just start them up. Program 2 says, okay, look, I'm finished for now anyway. I'm going to do some input and output. And the environment says, okay, program 3 will start. You'll notice that as program 3 is going, program 1 is waiting. Program 2 is still doing its input and output request. And at some point, program 1 is finished waiting, it's done its job, and then it says, okay, is the CPU ready? At this point, is it ready? Yes, program 3 has given up the CPU, it's doing input and output, so now you can start executing this one. Is this more efficient than just letting program 1 go and wait for input and output? And yeah, you're going to get more done in this environment. Is it more complicated? Yeah, you need to build some extra things into this. There's a bunch of stuff that we just talked about there that's kind of implied, so we'll tease that out here. So a process can be in one of 3 states. First one is, well, when you make the process, it's automatically ready. You can do something with it. You've made it, it's available. Once it's available, and there might be a bunch of these, you can schedule one of them and you can put it on the CPU. You can pick one and make it run. So now it's in the run state. When it's running, well, it could be the last thing it's done. So you could terminate this process. It could stop and get deleted from the environment, right, because it's finished. If it's not finished and it's running, eventually it will say, okay, I need to do some input and output. The typical cycle will be do some work, save it, or load something else up. Do some work, save it, or load, right? That's the kind of dynamic you're working with. So when you run something, eventually it will do an I/O request and it will be put into the block state or the waiting state. Right? So it's no longer able to use the CPU and it's waiting for the input and output, and then it will eventually be granted that input and output, and once that's done, it will be ready again. It will be available to be put back onto the CPU. See how that kind of works? There's like a cycle. So what that means is you have a bunch of programs or processes that are ready. One of them is chosen to run on the CPU if we're using a single core environment, and then eventually that one will block and it will become ready again. When it's in the block state, you can pick someone else. Right? That's basically another way to view the previous diagram I showed before. So the task of deciding which process to run next during multitasking is called scheduling. There's a whole bunch of different options. We're just going to look at 3 basic ones, but any way you can organize these, that will be a scheduling algorithm, right? So the first one is really easy. First come, first served. If you are the first one here, you will get to go first. That sounds like when you're at the shops, right? You want to buy something and there's a line of people. The person at the front gets served first. That's fair, yeah? Is it always the most efficient? No, and you probably had this experience where you're waiting at the supermarket checkout and there's one person at the front and they're first, but they've got a gigantic trolley, right, with 100 things in it, and there's one person after them with one thing. Right? What would be more efficient? Having the person with one item go first, right? Because the average waiting time will be less. Does that make sense? If you're that person with the one item, you will definitely understand, right? So first come, first serve, yes, it's fair, but it might not be that efficient. You could have the explicit priority. It's like, well, actually, no, look, I'm more important than you. I'll go first. All right? Would you like that in a shopping center? Probably not, right? But there might be environments where that's actually appropriate, right? For example, I don't know, if you're in traffic and there's a police car that needs to get through, they will go first, right? So explicit priority could be used, but it's not necessarily fair in that sense. And if you have a really high priority thing and you keep scheduling it first, does anyone else get to go? No. So again, you have to adjust that a little bit maybe. The shortest remaining time. So this is probably the best one. This is the kind of example we talked about. Look, we got the guy with 100 items, and then we have someone with one item. The shortest remaining time would say the person with one item will take the least time. We'll get them to go first. All right. That's to reduce the average waiting time. Now, the problem with the shortest remaining time in a computing environment is you don't know how long something will take to run. You don't know how long it will use the CPU next time. It might be short, it might be long. So you might have some complicated algorithms to check or to average over time how long it usually uses the CPU. So this is actually maybe a little expensive, but if you do this effectively, you will reduce the average waiting time, so your throughput will increase. Right, so some of these might not be as simple as I'm making them out, I guess is what I'm saying. Next thing we look at is this idea of preemptive and non-preemptive scheduling. So an operating system can run several processes concurrently, but each must take turns accessing the CPU, right? So you can't run two things at the same time on the one core or on the one chip. If you have multiple cores, you can run, if you've got four, you can run four things, yeah? But we're going to consider just the single version here. So some operating systems will allow each process to decide when it wants to let another process access the CPU. I referred to this before, where you can't tell the job to get off the machine. It'll stay there unless it says, I'm finished. Okay, that's nice for that job, but if something goes wrong, you will never get the CPU back. All right, so it's a little bit fragile, I guess, in that sense, in terms of the overall performance of the system. A preemptive operating system, on the other hand, will say, okay, you get this much time. You get 10 units of time, whatever that is, and once those 10 units are up, you're off. And you can't stop me kicking you off. Right? So you actually don't own the CPU, I own it, and I'll give it to you for a little bit, and then I'll put someone else on. So preemptive scheduling basically says, okay, we've got a job, you get a little bit of time, then the next job runs. So basically it interleaves the processes. There's a timer that you need, because you need to know how long it's gone for. And there might be a process priority that you're using. So maybe higher priority processes get to go first or get to go more often. Interrupts generated by the timer are used to involuntarily remove the running process from the running state. So you notice that the process doesn't have any control here. It's just using the CPU. The operating system has a timer. The timer goes off. That interrupts the CPU. The CPU can't stop that interrupt. Right, so then you process the interrupt, and the interrupt says take this job off the CPU and put a new one on. Right, so it's the control is taken away from the process. The scheduler will then work out which other process that is currently waiting, or sorry, I should say ready to be run, to run next. And there's an algorithm it'll process for that. And there may be several algorithms depending on the kind of scheduling it's doing. So input and output requests are interrupt driven. So that's when a process wants to do an input and output function, it generates an interrupt as well. So there's two cases here when you can get kicked off the CPU. One is your time's up, you're off. The other one is you have decided that you want to do some input and output, you voluntarily release it. But they're both interrupt based. So as a picture, you'll see here that this program 1 is executing. There's a timer interrupt. So at this point, it's used up all its available time. It's then waiting. Now, at this one, we don't know whether it was using the input and output or not, but let's just say the timer interrupt was there because its time is up and not because it asked for input and output. Then it's just sitting there waiting. It can't do anything. It's not able to use the CPU. Program 2, you notice it doesn't start executing straight away. There's a delay, and that's because the operating system has to do a number of things. It has to say, okay, look, you are running. That means you have some information in the registers. I probably need to save those. So when you come back, you can just start up again. I also have to check who should go next. That takes a little bit of time. And then I apparently have picked program 2, and they can run now. And that happens every single time that the timer interrupt occurs. So if you look at this red thing here, should this be a long or a short time? Short, very short actually, because you do it every time there's an interrupt. So if you have a 5-second timer and this red bit takes 5 seconds, you have halved the speed of the machine, right? Which is probably not a good thing. So it should be quick, basically. So you might not make as good a decision as you might if you have more time, I guess is one way to look at that. And so that's that diagram. Dispatching, I just already mentioned this. When you've got a process, like process A, B, C here, there's three of them. Process A is running on the right. The scheduler comes on and it says, okay, the timer has gone off. I need to kick you off the CPU. That means I have to save your registers. Once I've saved your registers, I select the next process, and then I restore the registers of that next process. Does that make sense? I just reload its state so that it can just start up. Okay, and it does that over and over. It does the same thing for process B once the interrupt occurs, and so on. That process is called context switching. The reason is each process has a context, what it understands about the world. When you kick it off the machine, you have to save that context. When you put it back on, you have to load that context back up. Moving on to memory management. So manage allocation and freeing of memory used by running processes. It's used to protect one process from being corrupted by another process. Do you think that's important? Absolutely, right? You've got all these programs running around. If you don't protect the memory from other programs, right, they just read and write from the memory of a different program, which potentially will have some really bad consequences. You might get some pointer exceptions. Depending on the environment you're running in, you'll get some kind of problem, some warning if a program tries to do that. If you have a small main store, so you have a small bit of RAM on your computer, then I already mentioned with the Photoshop example, if you don't have enough RAM to run Photoshop, for example, you can still run it, but you won't run the whole thing. You just run part of it, and then as you need other parts, you'll have to load them up as you go. So do you think that's slower than if you had everything in memory at once? Yeah, there's a delay, right? If you haven't got something, you're going to have to get it. Ideally, you don't notice the slowdown. Yeah. It's used by multitasking operating systems to make it look as if each process has sole control of the CPU. Here is an example of a problem. Have you ever seen one of these? Most likely. And what's it saying? Invalid access to memory location. So this is a problem where it's tried to access some location that it does not own, it doesn't belong to it. And it says click, retry, ignore, or abort. Have you ever had a good outcome with this? No? So probably once it's in this situation, probably the best thing is just to kill the program, right, and start again, because it's difficult to recover from this kind of problem. So here's the memory allocation examples. So when a process starts, it's allocated a chunk of memory and loaded into it. When the process ends, it's deleted from memory and it leaves a hole. And if you do this over and over and over again, that you get all these little holes spread out all the way through the memory. This sounds suspiciously like when you're working with a disk drive and it fragments, and you so now and again have to defragment your hard drive, for example, because you've used it so much that it leaves these little gaps that it can't fill properly, and you need to sort of reorganize things. So in this case, memory and hard drives are very similar in that logical view. So any new process will be loaded in the unused memory, but if it's too big to fit into any single block of free memory, it will be fragmented. So multitasking systems rapidly run into memory allocation and memory fragmentation issues. There's a diagram here that sort of shows you that, but I'll show you a slightly different one, just to visualize it really easily. So we start off with 500 spaces. I add A, and A goes here, and it's worth 200. So what's left? 300, right? So 300 free. It's 500 free at the moment. I add B, so here's 200, and here's 250, and what's left? 50 free. Now I remove A, so I'll call this A and B here. So A is gone, so this is still 200, and it's now free. B is 250, it's still there, and this is 50, which is free. What's the total available space? 250. Yeah. I now get C, and C is 210. Will it fit into memory? It cannot fit into memory because there is no hole big enough for it to fit into. I have to split it up. Does that make sense? So even though there's technically enough space, 250, because of how it's organized, I can't use it that way. So what I should probably do is defragment this, and I could probably move B to one end, yeah, and then I would have 250 on this side. Does that make sense? Move it to the top, I could move it to the bottom, I could move it to the middle. There's a lot of different ways I can organize this stuff, but it would involve me squashing things up on one end somehow. Yep. Okay. So this is the idea of fragmentation. I'm pretty sure most of you have run into that with hard drives, defragmenting hard drives. It's a similar kind of issue. So virtual memory is the next topic. Basically, it makes it appear that there's much more physical main memory than you actually have. So if you've got a 2 gigabyte machine, you can pretend that you've got a 16 gigabyte machine. Do you actually have that memory? No? So that stuff has to go somewhere. Where does it go if it's not in the memory? What other places do you have to store things? A hard drive? Or a solid state drive? Or some secondary storage that you have? Is the secondary storage slow? Yep. So again, the speed of this might be impacted. So what we have is this idea of paging and framing. So what you do is you chop your memory up into equal sized chunks. Let's say they're 4 kilobytes each. So your memory is 4 kilobyte chunks, and what you do is the same thing with your programs. You chop it up into 4 kilobyte chunks. That means that any chunk from any program will fit in any frame in the memory, because they're all 4 kilobytes. Does that kind of make sense? You just have regular sized shapes. So what that means is you can move them around anywhere you want. So virtual memory works by splitting main memory into these physical pages, and then the program has as many logical pages as you want, as many pages you need. They won't all fit into memory, basically, though. The operating system will use the secondary memory, like the hard drive, to store the information that can't fit into memory, and it will have to map. Well, if something is on the hard drive and it's not in memory, when you need that part, where is it? How do I get it quickly? Right? You have to have some kind of mapping. So here's a diagram that shows you a little bit of the mapping. You'll see in the middle, the yellow thing is the pages that are stored on the disk. Those are things that are not on or not in the memory. So those are the light blue pages, C, E, F, I, and J in this case. The dark blue ones, A, B, D, G, H, they're actually physically in memory. Right? So they're actually in the slots that are in memory. Is that the whole program in memory or not? No. So if I need to use A, D, G, B, or H, it's great. They're in memory. I can just use them. What happens if I need to use C? It's not in memory at the moment. I will need to load it into memory. Now you'll notice my memory, I don't have any free spaces. I would have to kick out one of the ones that is in memory at the moment, replace it. Yep. And if that has been changed, I might need to save what's there into memory, or sorry, onto the hard drive, to make sure that it's captured, the changes. So there's a table on the right that shows you the logical page, which is the program, how many pages it has. It has the physical page, which is the actual memory location, and then it has, is it in memory or not? That's the present bit. Okay, that's for one program. You can imagine that it gets more complicated with more programs, right? So if you have more programs, you probably allocate less space to each program so that they still fit at least partially into memory. Okay, looking at software applications. Software applications are programs that a computer executes to perform specific tasks. Those can be stored in memory as either machine code or source code, and applications stored as machine code have been modified in some way. You wrote them in a high-level language, and now they've been translated using a compiler, usually, that translates it into something that the machine can understand. Applications that are stored as source code, on the other hand, have not been compiled, and they will be interpreted. There'll be another program running while you run your program, which takes the instructions and does something with them one at a time, usually. So the kind of example that we're talking about there is Java. Java is an interpreted language where there's a Java virtual machine running that just takes the instructions from this Java source code that you wrote, and it interprets those as it goes, and it does the program a bit at a time. Programming languages have evolved from machine code. We typically don't write stuff in machine code. You certainly can, right? But there's not that much need for it. Mostly we like to write things at much higher levels. English-like statements, actually. And you'll see that when you look at Java or C or any of those. They're still a little bit terse, but they have English-looking words in them, right? And some symbols, typically. So machine language, binary code, assembly language, mnemonics, so little short English codes, basic JavaScript, Perl, Python, Fortran, COBOL, Pascal, C. They're all different levels here. As you go through and you do more programming, you'll run into some of these models, I guess, right? But typically when you're writing programs, you'll be working towards the higher end of this table rather than the lower end. Virtual machines, I already mentioned really quickly. The Java is designed to run on a virtual machine. At the moment, I am running a virtual machine on this computer. I'm running a Mac, but I'm running Windows. Right? So this environment is pretending to be an environment suitable for a Windows environment. Does that make sense? And so, is it slower than if I just used the Mac, do you think? Yeah, because the Mac has to run this software. So these environments are typically slower, but they allow us to pretend that we're another kind of architecture. So if you look at the bottom right there, you'll see that there is a computer hardware, the kernel, device drivers. Have we seen this before, this diagram? Yep, we saw it in a few slides ago. There's a service layer, there's a command layer, user application, so those are the normal programs. And then you have the blue Java virtual machine box on the right. That's a program, it's a user application, and on top of that is your actual Java program. So there's an extra step. And it is an extra step because it has to be translated or interpreted into the actual instructions. So virtual machines are similar to interpreters, but they process binary instruction codes instead of high-level source code instructions. And the virtual machine instruction codes in this Java programming example, they're called bytecodes. You semi-compile the program into a lower level state. So virtual machine code runs slower than the native code because it's interpreted, and it will use more memory because you have to run an extra program to make it work. So in summary for this section, we looked at the history of operating systems, process management, CPU scheduling, and memory management. Next time, we'll start on the networking section of the course, so that'll be computer networks. And that's the end of this section.